Good evening, everyone. Welcome to the NPTEL live session for week 7. So, uh, today we will be finishing this cyclic circular dichroism topic on the application part is left. And today we will be introducing the spectroscopy, not in full details for the Mossbauer spectroscopy that would be started from the next session, but a kind of just for all the spectroscopy that we have in hand. Say, for example, NMR, EPR, IR. So, but before starting the lecture, if there is any question or any doubt you guys are having regarding what we have studied so far, please let me know so that we can then move ahead. I'll wait for a few more minutes for others to join, then we can start the session. Thank you for joining. So we can start it now. So as I have already explained that what topics we are going to cover, so we'll start with the applications of CD spectroscopy. So far, we have seen a lot about CD spectroscopy. So just a brief that I introduction or a recap I should give it to you. So we were talking about the electricity positive and negative, and we discussed it in the proteins, mainly secondary structures, which is the alpha helix, beta sheet, and random coil. So that is one of its application. We can easily identify which kind of secondary structure is being formed over there. So the signature for the alpha helix goes from positive and coming to the two negative bands around 190 nanometer. This is at 208 nanometer and 222. Then if we talk about the beta sheet, that would also start from the positive end, giving at 195 and a peak, a broad peak at 218 nanometer, which is in between the two. And this is 195. Whereas the signature of random call is easy to interpret because it starts with the negative end at the same position as it starts for the beta thing. And but it gives a peak, which is a very broad peak and also in the similar region of 200, 220 to 230 nanometer. So this is one such application where CD spectroscopy helps in identifying the secondary structure of the protein. Also, if it's a mix or it's a hybrid kind of system where we are having both alpha helix as well as the mixture of alpha helix plus beta sheet, that also we can be able to see from CD spectroscopy very easily, which is not possible in case of optical spectrum, because there it would give you more or less a similar spectrum, just the intensity or little shifting is there, but to be very defined regarding where the alpha helix, how much beta sheet, whether there is a mixture of the two, so that we can easily see from the 3D spectroscopy. Now coming to real application when we are dealing with molecular complexes. So one such thing is if we are treating a cobalt-based system, which is having an amino acid chain of A, C, D, L, T, C, G, we already know that these are the one-letter codes for amino acids. And when it is treated with oxygen, that means it is getting oxidized. So firstly, oxidation of the thiolate, which is connected to it, that would happen, followed by the oxidation of your cobalt. And this kind of feature is being seen, the 3D spectra helps us to understand or identify. What it helps us to identify, it actually shows bands. And when 3D spectra is showing bands, that means there would be a chirality which has been induced. And that chirality comes from the charge transfer bands. So charge transfer is happening in this particular system on treatment with oxygen is being confirmed from the circular dichroism. So what really happens is we have a cobalt center in +2 oxidation state. We are taking a thiolate over here, which is connected to amino acids. Here also we have nitrogens connected to amino acids, and so this is connected to amino acids. Okay. Now, when you are treating with oxygen, so as we said that this particular group, that thyroid would first get oxidized. So what we will be ending up, the cobalt oxidation state would remain the same. One of the phthalates get oxidized to S double bond O and double bond O. Nitrogens and other nitrogens would remain as it is, right? Now, when you are again given more access of oxygen, the this center, which is your cobalt, that will now be converted to cobalt 3. These things remain constant. Now, since it is a cobalt 3, when we are taking the ligand over here, so this becomes a metal which is having more oxidation state, and thyroid, we know that it is having electron density which it can transfer to the cobalt. So we can expect here to have ligand to metal charge transfer from S negative to cobalt plus 3, and this charge transfer can be easily identified in CD spectrum, right? Now the second application that we have in hand is, since we know that CD spectroscopy shows changes at different pH, so that is easy to comprehend, like effect of pH on the rate of catalysis, whether it is increasing the rate, it is decreasing the rate, or it is remaining constant. So that effect can be easily seen in CD spectroscopy because it does change with the spectra, does change with the change in pH. So here also we are taking a cobalt example complex where we are having this kind of ligands where the nitrogen is connected to its amino acid group. This is a carboxylate, and again this is a carboxylate. When we are having a carboxylate, this is having a tendency to coordinate with your cobalt. But when we are introducing the proton source that is at pH less than equals to 3, what really happens, these carboxylate groups, this carboxylate group, which is free to bound with your metal center. Now at in acidic conditions, particularly at certain pH, what it would look like. So this carboxylate now becomes OH. Similarly, here also it becomes OH. So once this is OH and we are giving another proton source, H positive, it would protonate your OH to release H2. Therefore, hydrogen reaction happens, right? So pH really matters when we are dealing with the amino acid containing complexes, and CD spectroscopy is the one that would really help you to see the changes over here. Now the reason behind, as I already said, we have already explained like why with the certain pH it is changing the increasing the catalysis. So another topic that we have in hand is the amino acid isomerization. So we know that if we have so we know the Corn rule for defining whether it is L isomer or D isomer. So it has to be 1, then 2, then 3. If you give here number 1, number 2, number 3 being the hydrogen at the back position. So it is going an anti-clockwise. So this is an L isomer. Now, if we form the mirror image of this one, we will get C. H would remain at the back position, whatever it is, it's front. We are getting NH2 here, R here, COH here. And if again we'll name it 1, 2, and 3. Now it goes from this is your clockwise, which is D amino acid. So racemic mixture means that we are having both L amino acid in equilibrium with D amino acid, or both are present in 50% population. So in that case, we should be able to know that what is the amount of which isomer is present over there and what is their half-life. So there is certain chart for half-life of certain amino acids. So when we are having amino acid and the half-life, so basically what happens, like L amino acid slowly converts to D in presence of water. So half-life is the time which it is going to take, the half time which is going to be taken to convert to the amino acid. Histidine, if we have, that has the lesser half-life compared to tyrosine, then alanine and valine. So our question is, why are the half-life values are different for all of them? If we take the general case where we have an acid group, alpha carbon with R group, and the amino acid, and at the back we are having H, which is L form. We just saw that. In presence of the water, the equilibrium is in positive forward direction. So what really happens is this water takes up the proton and gets H3O positive. So in presence of water, it exists as a Zwitter ionic form, and that H positive is being transferred to the NH2, making it NH3 positive. So this is basically a Zwitter ionic form where the charge separation we can see. So once this charge separation we are having, followed by when we treat it with again an acid source, the oxalate gets attains its position and converts to the acid is retained and we get the NH3 here with H, followed by so this can be in equilibrium with the O getting converted to OH, which means the reduction, and they are forming a serial bond C. Now at this stage, it has attained a plenarity. When plenarity is there, it's no longer chiral. Now this becomes again in another form where we are having HO, C double bond O, C attains negative charge, R and NH3 positive. So this carbon ion now is again a planar structure. So it can have both the isomer. So this carbon ion is planar. So therefore it can form both isomers. Firstly, it will be having CORH, NH3, which is your L amino acid, and it can attack from the other end also, where CO NH3 is this side, R is this side, and H. So this is your D amino acid. So in the racemic mixture, you get a 50-50% of both the things when we are describing how it, in presence of the proton or in the presence of water, how it converts to from the L to D amino acid. Slowly, the L amino acid would definitely convert to the D amino acid. So again, coming back to our main question that in case of histidine, why the half-life is less if we compare it with anybody. So we have an alpha carbon, which would be having NH2COH, and this is the chain CH2 and a 5-membered ring. This imidazole, so what really happens is electron movement, that lone pair movement, that happens towards the ring, and Therefore, it stabilizes the carbon ion intermediate because whatever the carbon ion is being formed over here, so this would go onto this ring. The movement would be in this side because we are having a more electron negative effect over here. So when it happens, so it would stabilize your carbon ion. Once it is stabilizes, when something is getting stabilized, that means its half-life is increasing. The time for it to be staying at carbon ion, that would be increasing. So there would be high rate of racemization, and where racemization is there, so half-life, the time that it needs to convert from L to D, it would be very less. It would be so fast that it does not stay for very long time in its original form. That's why in case of H3, it goes very fast. Now, with this one, our application for the series spectroscopy is finished. I hope you guys have understood so far. So now we come to the another topic, that is the spectroscopy part, which would help you to understand when we will be talking mainly about this Mossbauer spectroscopy. So spectroscopy, it's basically, if you talk about a spectra, that would give you a plot in all the spectroscopy I'm saying between intensity and energy. Any spectroscopy, if you'll take for that matter, it would always be a plot of the y-axis is your intensity and the x-axis would be energy. And we know that energy can be written in different forms. In terms of wave number, we can define. In terms of wavelength, we can define. So, so in this case, intensity means it's a quantitative value where we got to know that how much is the concentration. Whereas if we say about energy, it's a qualitative term which tells about your sample, properties of your sample, right? Now there are two different ways to represent the plot. One is the optical spectroscopy, which we call as the absorbance one in terms of absorbance. Or the second one that we have is your FTIR or IR spectroscopy, which is explained in terms of transmittance. So if we'll take the first one, the absorbance you have already seen, we'll be having a lambda nanometers, and you see a plot like having different peaks. Similarly, if we have the IR, you would be having the transmittance, percentage transmittance. So whatever the peak you are seeing over here, at exactly same point, you can expect your peaks to come. So transmittance would give you exactly that tip where you are expecting your wave number value. These are the two ways that we expect, and we know that transmittance is inversely proportional to your absorbance. So whatever we are seeing over here, that goes in reverse into the transmittance. So there are two different ways where we can represent our any spectroscopic plot, be it in transmittance form or absorbance form. Now we start with our first spectroscopy, which is the NMR spectroscopy. Nuclear magnetic resonance, NMR. As the term suggests, that it deals with nuclear magnetic states. That means it involves the I value. So if we have energy going this way and we have one state, I equals to, taking I equals to 1 by 2, can have Mi plus 1 by 2, Mi minus 1 by 2. So the plus 1 by 2 and minus 1 by 2 for I equals to half in absence of the field would remain degenerate. There won't be any splitting of these things. But if we are having in terms when we are giving the magnetic field onto the x-axis, with the increase in the magnetic field, these two states split into Mi minus half, Mi plus half, fits into lower and upper level. This aligns with your magnetic field, and this is opposite your magnetic field, and the total difference between these two would be the H. So this difference is matches when we are providing a radio frequency in NMR. When we provide the radio frequency and when it absorbs the frequency, then the transition from your ground MI level to the excited MI level happens, and therefore you see a signal. Okay. So it basically depends upon the field that you are giving and the nuclei. Say for example, we are having the I system, I equals to half. This is your nuclear spin. Just like your electronic spin. So this half value stays for proton 13C, 19F, 31P, etc. So for each nuclide, the frequency that is required will be different, and it will be adjusted by the instrument when you are giving certain parameters. Say you have for proton, the mu, the magnetic moment, is a property of the nucleus. It would be, since it is 2.7927, and the frequency, radio frequency that is required for resonance, it would be, say we are saying 500 megahertz. I'm saying that we are taking it in case of the instrument. For 13C, it would be 0.7022 and approximately 1 by 4th of what we are using for proton because of the chiral-magnetic ratio. For the 19F, 1.6273 and 470 megahertz, closer to what we see for and then 31P we have 1.1305 202 megahertz. So depending on the different nuclei, it would be having a different resonance frequency that would be adjusted when you are giving those parameters. What would happen if we are dealing with the electron spin resonance, or EPF? So another spectroscopy. If we deal with energy S equals to half system, which would be split it into ms plus half and ms minus half, then the delta E would be equal to G beta B naught, where this is your spin state and it requires microwave frequency. This also tells everything about your system, the oxidation state. Moving ahead with your third spectroscopy, which is IR or vibrational. Where we generally see a bell system where we are having different vibrational levels, the ground state and the excited state. This is excited, this is ground state, and the energy is frequency plus half into h nu. So here is the E and here is your reaction coordinates. So this also works at microwave frequency, where the transition happens from your one vibration level to the another vibration level of the excited state following certain rules. So this is happening for the IR. It would tell you about the functional groups, various functional groups present, because that would appear at a certain wave number. So now what we have seen the sequence, the NMR requires radio frequency, which lies in 10 to the minus 5 electron volt, followed by you have vibrational, which is the microwave, proximity 10 to the minus 4 to 10 to the minus 3. This requires by ER, IR and EPR. Then you have the optical spectroscopy, so which is in a range of near infrared, visible and UV. And it's approximately 0.1 to 100 electron volt. The energy is increasing. Then we have X-rays, which goes from 10 to the power 4 to 10 to the power 3 to 4, requires for single crystal XRD. And lastly, we have the gamma rays. Cosmic also are there, but our spectroscopy is dealing with the gamma rays mass, 10 to the 4 electron volt. So highest energy rays that we are having is your gamma rays. And when we are dealing with the gamma rays, so when we are dealing with gamma rays, it would change your nuclear states. And that leads to the Mossbauer spectroscopy. So what really happens is, when I said that I was having I equals to say 3 by 2 and I equals to 1 by 2, this is my energy. Now this in presence of, these are two different states and spin states, and in presence of the magnetic field, when I'm giving a magnetic field, this will split into Mi minus by 1 by 2, Mi plus 1 by 2. Similarly, the above one would also split into 4 minus half minus 3 plus 3 half plus 1 half minus half and minus 3 by 2. So the transitions in the radio frequency, or in NMR, the transition happens within the nuclear state, whereas when we are providing the gamma rays, transition really happens between two different nuclear states, which is I equals to half to I equals to 3 half. So we can't really get confused over here. This is mm, very minor thing, but we need to be very careful. So what I said is, so in presence of the radio frequency, that is for the NMR, transition happens between the same I states, nuclear spin states, whereas in presence of gamma rays, which we are saying that is for Mossbauer, transition happens between, after the resonance, it happens between different I states. So be very careful with this terminology. And with that, the introduction to the various spectroscopy is done. If you have any questions, please let me know. Otherwise, we can take up the assignment questions. Okay, so the questions are pretty straightforward. If you understand the concept, you will be able to answer it. So which of the following statements is or are right? Histidine has more half-life compared to valine because the imidazole group stabilizes the carbon ion. We have already discussed that the carbon ion stability, the half-life is dependent. Half-life means of any amino acid means that the half time that it is going to take to convert to L to D. So L to D is only possible when carbon ion is stabilizing for a very long time. So more stability of your carbon ion, lesser will be the half-life. In case of histidine, we have that imidazole group, and that imidazole group made sure that carbon ion is stable for a very long time, and therefore its half-life is very, very less. So the second option is right, where the half-life is less compared to the valine, because valine does not have any imidazole containing aromatic group. It's simple aliphatic chain. So therefore, it can't stabilize the carbon ion for more time, and it stays in L amino acid compared to the D amino acid. So which of the statement is or are right about NMR spectroscopy? In NMR, the transition happens between the same nuclear states with opposite spins. True that. Radio frequency is used for different nuclear. Radio frequency so required is same. The active nuclei should possess I value greater than or equal to 0. So I, if it's 0, then it can't work. And radio frequency so required is not same for every nuclei, it's different. And radio frequency is used, that is right. And the transition happens in the different same nuclear spin states with the opposite sign, that is correct. Arrange the following EM radiations, that is electromagnetic radiations, if they're in decreasing order of energy. So we know that gamma is having more then visible, then microwave, then radio. We just saw that. Here it is, this one. So this is gamma, then your visible, then your microwave, and then your radio. So gamma, visible, microwave, and radio, it's right. So choose the right option for the Mossbauer spectroscopy. Gamma radiations are used to transition between different nuclear spaces are used to electronic nuclear interactions are called as hyperfine. That is also true, and hyperfine interactions are weak. That is true. So all of them, that holds true here. The hyperfine interactions, that means when will be employing the electronic part and having the combination of both magnetic as well as electronic part, there would be electronic nuclear interactions that we will be introducing in our coming slide. So with that, our the discussion is over for today. The session would be continued for next 20-30 minutes more for having a discussion from your end. If there is any doubt that has not been cleared so far, please let me know. We can have a detailed discussion on that. Thank you.